flow in non-circular ducts. If the duct is non-circular, the analysis of fully developed flow follows that of the circular pipe but is more complicated algebraically. For laminar flow, one can solve the exact equation of continuity and momentum. For turbulent flow, the logarithmic law velocity profile can be used, or so we can write for laminar flow we can solve the exact equations of continuity and momentum. For turbulent flow, the logarithm law velocity profile can be used, or the hydraulic diameter is an excellent approximation. So, in the logarithm law velocity, we have formulation for logarithm law. Profile can be used, or the hydraulic diameter is an hydraulic diameter the hydraulic diameter conception. For a non-circular duct, the control volume concept in the figure here the cross-section area does not equal to a circle, and the cross-sectional perimeter weighted by the shear stress. Now we have the perimeter in this type of problem, and also a cross-section. Not circular. So we can write the non-circular the momentum equation for this picture. The momentum equation contains force component. The first force due to the pressure difference. The second is due to the volume of fluid gauge, and the shear stress forces that shown with toe wall, and multiply to the application parameter with P delta N. In the equilibrium should be equals to 0. Or we can have this relation, the head loose in the plus delta Z, which is equals to this is an identical equation which are also described before. There are two notes here that the shear stress is let me write the relation again here. The head is a non-circular one. The shear stress is an average value integrated around the parameter the length scale takes the place of the pipe radius R. R in the circular for this reason, a non-circular duct is said to have a hydraulic radius which is equals to hydraulic radius R H equals to A on P, which is equal cross-sectional area on wetted perimeter This concept receives constant use in open channel flow also in chapter 10, where the channel cross-section is almost never circular. If we comparison the previous equations for pipe, we define the friction factor in terms of average shear stress. So, friction factor for non-circular sections equals to where NCD is non-circular ducts and V equals to the volume flow on cross-sectional area, and we can also have a relation for head loss in the non-circular ducts. RH V2 on 2G. This is equivalent to the equation for the pipe flow, except that D is replaced by 4RH. Therefore, we customarily define the hydraulic diameters as so for a replacing D with RH, we have this relation for non-circular duct. The hydraulic diameter is 4A on the wetted perimeter, which is 4 multiplied to area and wetted perimeter, equals to 4RH. We should stress that the wetted perimeter includes all surface acts upon by the shear stress. For example, in circular annulus, both the outer and the inner perimeter should be added. The fact that DH equals to 4RH is just one of those things. Chalk it up to an engineer's sense of honor. Note that the degenerate case of circular pipe, we can write DH for circular pipe. The area is by R2 and the 2PR, which is equals to the. We would therefore expect the dimensional analysis that the friction factor F based on hydraulic diameter that is stated in previous equation, which was we have a relation for HF, a function of the friction factor so we have a Reynolds we correlate with the Reynolds number and roughness ratio based on hydraulic diameter. We can write the function of friction factor as 2 9-dimensional and epsilon on DH. These two are Reynolds. These two non-dimensionless parameters are well known, and this is the way that the data are correlated, but we should not necessarily expect the Moody chart to hold exactly in terms of this new length scale. And it does not, but is surprisingly accurate with this relation, conditional relation, which says that for non-circular ducts, the friction factor can be computed from this relation. DH if the laminar flow and for turbulent flow we can use the Moody diagram of the value Reynolds and epsilon on DH with 15% error. Flow between parallel plates is the next description in non-circular ducts.